Hello everyone, thank you for coming. My name is Nitinraj and today I and my colleague Aayush is going to present RIT-Eyes rendering of near-eye images for eye tracking applications. Modern video-based eye trackers use infrared cameras to monitor movements of the eyes in order to gather information about the visual behavior of the individuals engaged in various tasks. Contemporary algorithms for estimating gaze direction rely heavily on semantic segmentation of specific regions of interest in the eye images, such as the pupil. Segmentation is complicated by the presence of corrective lenses or by reflections of the surrounding environment, eyelashes, and illumination. Deep neural networks for video-based eye tracking have demonstrated resilience to noisy environment, strange reflections, and low resolution. To train these networks, a large number of manually annotated images under various conditions are required. To elevate the cumbersome process of manual labeling, computer graphics rendering is employed to automatically generate large corpus of annotated eye images under various conditions. Reconstructing all the parameters that influence the imaging of an eye is a very difficult task, and it is common to make simplifying assumptions regarding its structure. Let me explain the major components of the eye. So the black portion that you see over here, that is called the pupil, and the colored portion is called the iris, and the white section over here is the sclera. This is the skin. The small pink nodule is called the lacrimal caruncle, and the hairy portion is called eyelashes. A rendering platform incorporates 24 head models with varying skin color, gender, and ethnic group. 8K resolution color maps with high-quality cameras were used. To approximate the properties of human skin in the infrared domain, the red channel from the original diffuse texture map is incorporated for rendering purposes. Another important contribution is modeling physiologically accurate corneal bulge. In the previous works, they have used a spherical cornea, but the corneal surface of a real eye is aspherical, and we have used this formula for modeling the cornea. Additional testing is required for evaluating the importance of using aspherical cornea versus spherical cornea. To mimic human behavior, whenever there is an eye rotation, we are deforming the eyelid depending on the type of eye rotation. If it is a vertical rotation, for example, if the eye is looking down, then the eyelid should follow the eye. We are not just changing the eyelid position, we are also changing the skin texture around it to have that stretching effect using blend and shape keys. The other type of deformation is caused due to the corneal bulge. So whenever there is an horizontal eye movement, the corneal bulge is actually pushing the eyelid around. We have a video to show that. On the left, we have a real eye video from Gaze and Wild dataset, and on the right is a synthetic version of the video. And you can see the eyelid deformation caused due to the corneal bulge. Tear film. The reflections are caused due to the light source from the eye tracker. There is a thin layer outside the eye covering the entire eyeball. In the previous synthetic rendering, as you can see, the reflections are very sharp. But if you compare that with the real eye images, the reflections are not that sharp. So for that reason, roughness was added on the tear layer, which smoothens the edges, giving it a streak effect on the reflections. Previous datasets have modeled the pupil as an opaque black disc. The pupil in our eye was modeled accurately as an aperture such that the constriction or dilation of the pupil was accompanied by the appropriate deformation of the surrounding iris texture. Retroreflection. Let me explain what is retroreflection. In a reflective surface, when a light is incident on a surface, it reflects and goes away in the opposite direction. But in the case of retroreflective surface, the reflected light returns back to the light source. Some eye tracking methodologies depend on bright pupil for pupil detection. The bright pupil response occurs when the light source is within 2.25 degree of angular separation from the emerging optical axis. This shows the bright pupil effect at varying degrees of angular separation between the emerging optical axis and the light source. Caruncle. Lactomal carbuncle is a small pink nodule positioned at the inner corner of the eye. The carbuncle consists of skin and sweat glands. In contrast to previous work, we have used carbuncle in our renderings. Reflective eyewear. Other works have not used reflective eyewear in their renderings. If we are using glasses, then causes an additional reflection on the glass, which may affect the performance and cause problems during segmentation. As you can see, the reflection on the synthetic rendering is covering the iris edge. So 50% of the rendered dataset contains glasses. Environmental reflections. In order to induce environmental reflections, 360 SDR images were used. These image textures are mapped onto a sphere with the eye model at the center. Each pixel intensity acts as a separate light source. Let's move on to eye and image video generation platform. This is the RIT-Eyes rendering pipeline. There are three phases in this. The first phase is the texture phase, the second phase is the 3D position phase, and the last phase is the image generation. In the texture selection phase, you have to select the iris and the scalar textures. You also have to select the type of cornea that you need. And the second phase is the 3D data selection. So we have to select the gaze position of the eye in azimuthal and elevation range, and we also have to select the head orientation also in azimuthal and elevation. And after that, we have to select the camera properties like the position, the focal length, and the orientation. And once you have done that, then it moves on to the image generation phase, which is it generates three types of images. The first one is a synthetic image, the middle one, and 2D ground truth mask and the 3D ground truth mask. This is one example of static images that were rendered using the pipeline. The first one is a synthetic image, and the second and third one is a 2D ground truth mask and the 3D ground truth mask. This is one example of a sequential image that was generated using RIT-Eyes rendering pipeline. On the left, we have real video of the eye from gaze in wild dataset, and on the right is a synthetic version of that dataset, of that video. And as you can see, the problem with the RIT-Eyes pipeline is there's no blinks incorporated in them, and also it is not able to mimic the eyelid position of the real eye video. This is the user interface of RIT-Eyes rendering pipeline. So once you land on this page, you have to enter the type of head models that you need, and then you can add like 1, 2, 3, 4. There are 24 head models to select from, and then you have to enter the number of images that you need to render, and then you have to select the type of dataset that you want to render. For example, if you want just uniform distribution of all the properties, or if you want to generate the sequential video, or do you already have the 3D points that you want the data from, and you provide the data path. And the rest are the camera properties, such as the camera's azimuthal elevation range, the azimuthal range, the pupil radius, the focal point, the energy of the light source, and the eye pose. Let's move on to the datasets that were rendered using RIT-Eyes. Using RIT-Eyes, you can render images similar to images from publicly available datasets like NVGaze and OpenIDS. S denotes the synthetic version of the datasets rendered using RIT-Eyes. The first one was S-NVGaze, which mimics the camera properties of NVGaze. And the second was S-OpenIDS, which mimics the camera properties of OpenIDS. This represents a range of camera locations in the synthetic dataset. First column is S-NVGaze and the second column is S-OpenIDS. The green represents the elevation range of the camera, and the red represents the azimuthal range of camera location. You can also replicate the camera properties of People Core eye tracker with adjustable camera position and orientation. We can also render images in simulated infrared and RGB domain along with control and naturalistic setting where there are environmental reflections. So we have rendered two datasets, S general with control settings in IR domain and S natural with naturalistic condition in RGB domain. This represents the camera locations used in these two datasets. This is a comparison of range of camera position across the four datasets. Now my colleague Aayush is going to take over about the utility of the dataset and ML models that were used. Thank you.
Thank you, Nitin. So an important question is, how can we use this dataset? RIT-Eyes provides accurate ground truth annotations such as 2D, 3D segmentation maps, eyeball centers, and gaze direction to train a variety of neural network for eye tracking applications. In this paper, we present the baselines for the 2D semantic segmentation. 2D semantic segmentation has been shown as a useful estimate to predict gaze in some of the recent appearance-based models. For semantic segmentation, we explored two model architectures, SegNet and RIT-Net. Our previous work, RIT-Net, achieved state-of-art in 2019 OpenEDS dataset. Note that for training both the model architectures, we use the data augmentations and loss functions proposed in RIT-Net. Various hypotheses are tested for cases where models were trained on a different combination of our synthetic data sets and tested in both the real and synthetic eye images. The first hypothesis is if the CNN generalized to hid models not present during training. The high score of above 95% suggests that a CNN specifically trained for use with a particular eye tracker can generalize well to previously unseen faces that differs both in the structure as well as appearance from the training set. Further, we also see that CNNs generalize beyond the spatial area they were trained. Here, the spatial area refers to the images represented with various positions and orientation of the camera. All of these values are above the global MIU value. Here, the global MIU value refers to the mean of all the IU values for our test cases. Additionally, we also saw that when trained with a combination of datasets such as SNVGaze and SOpenEDS and tested on a particular set, either SNVGaze or SOpenEDS, we achieved similar performance. We concluded that the sample size of 39,600 was a sufficiently dense sample size for training semantic segmentation modeling. Similar results were observed when models were trained in a narrow area and tested in a broader spatial area. The figure shows a narrow spatial area used for training and wide spatial area for testing. Next is the generalizability in the data set that we intended to mimic. Unsurprisingly, the performance was inferior to training and testing with our synthetic data set. So there arises question like, is it because of the manifolds of the camera position, or is it due to appearance? Camera position hypothesis seems unlikely, as we have shown that a wide spatial area was generalized when trained with a narrow spatial area. For appearance, it seems plausible. We observe a huge uncertainty in identification in scleral region, less than 50% for most of the cases. We were limited by the number of scleral texture used in our renderings. More scleral textures can be used in future to test its impact. We also compare the performance of SegNet versus RIT-Net. And if we are only comparing the accuracies, SegNet outperforms RIT-Net. But a small parameters count might be an important factor in some of the applications to achieve real-time performance. At last, we have also observed high pupil accuracy compared to other eye regions such as iris and sclera. Pupil region is an important feature for many of the eye trackers. In terms of eye tracking applications, the problem with current model datasets is the generalizability in real eye images. Mixing synthetic eye images with real with techniques such as semi-supervised learning to train on networks or use of GANs to refine images might be a way ahead. We have only utilized one scleral texture. Additional scleral texture could be used, but we were only limited with the publicly available data. Next is we only explored the semantic segmentation framework. People-centered estimation frameworks are still to be explored with these images. At last, our pipeline has still room for improvement with addition of features such as realistic eye blinks, mascara, so on. One such case is eyeglasses with powered lens. We have only considered the reflection of glasses, but refraction due to glasses is still under progress. Thus, to conclude, we present RIT-Eyes, a synthetic rendering paradigm to allow renderings for user-defined settings. Our work improves upon the previous work with addition of various features such as active deformable iris, aspherical cornea, retinal retroreflection, gaze coordinate eyelid deformation, and blinks. We have also proposed baselines for SegNet and RIT-Net for semantic segmentation tasks. We believe with techniques such as a semi-supervised learning, one-shot learning, and so on, we can train neural networks with this rich data annotations to improve eye tracking. Thank you.